All right. So we've talked about inverses of injective functions. We talked about that in 6.6. So let's talk about inverses of non-injective functions. So by injective, I mean one-to-one, right? So we've talked about the one-to-one property back in like 6.2 or something like that. So remember, being one-to-one means that for every output, there's only one input that maps to it, right? And we talked about functions that are not one-to-one. Functions that are not one-to-one fail the horizontal line test, right? So all functions have to pass the vertical line test, but they don't have to pass the horizontal line test. The ones that do pass the horizontal line test are one-to-one, and the ones that don't are not one-to-one. So, for example, f of x equals x squared is not one-to-one, as we've talked about. And consequently, it does not have an inverse. And there are a couple of ways to think about why this would be the case. So, first of all, let's assume that f of x equals x squared did have an inverse. Now, what would the graph of that inverse have to look like? Well, f of x equals x squared looks something like this, right? And we know that graphs of inverse functions have to be symmetric with respect to the line y equals x, right? So that means that the graph of the inverse, let me grab a different color here. Okay, so that means that the graph of the inverse would have to look something like this and like that, right? So if this is f, then this would be f inverse. That's what f inverse would have to look like. Now, what's the problem with that? Well, the problem with that is that f inverse is not even a function. Look, it doesn't even pass the vertical line test, right? So it's not a function at all. The problem that this causes is the following, right? So number two, we know that f inverse of b equals a if and only if f of a equals b, right? If you have a one-to-one function with an inverse, right, then f inverse of b equals a if and only if f of a equals b. So if we assumed that f of x equals x squared had an inverse, what would f inverse of 4 be, right? It would have to be an input value such that the output value is 4, right? It would have to be, so what number could you plug in here to get an output value of 4? Well, one possible answer would be 2, right? Because 2 squared is 4, but there's another possibility. It could be negative 2, right? Negative 2 would also be 4. So what is f inverse of 4? Would it be 2 or negative 2? If we say both, then f inverse is not a function, and you can see the confusion that this would cause, right? If we said that f had an inverse, then we'd have to be able to say f inverse of 4 is what number? Is it 2? Is it negative 2? Right? So it causes it causes confusion, right? So that's why only one-to-one functions have inverses. That said, we can often restrict the domain of a function that's not one-to-one so that it is one-to-one on its new restricted domain. For example, f of x equals x squared is not one-to-one, and therefore it doesn't have an inverse. But f tilde of f equals x squared, x greater than or equal to 0, this thing is one-to-one, right? The graph of it would look like just the left-hand side of this graph, right? This is f tilde, right? F tilde has a function, or it has an inverse, right? Because it's one-to-one. So the inverse of f tilde would be just the top half of this green graph, right? And that's a function. It's a perfectly well-defined function, right? So anyway, that's why only one-to-one functions have inverses. But the whole moral of this section is that even though non-injective functions don't have inverses, you can restrict their domains so that the function on the restricted domain does have an inverse. Okay, so let's find the inverse if it exists. So let's say that f of x equals x plus 1 squared. Obviously, this is not going to have an inverse, right? It's just a parabola. It's been shifted left 1 unit. It's not one-to-one. No inverse. Right? It's not one-to-one. Okay, but now look at part B. Part B says, well, find the inverse of, okay, same thing, x plus 1 squared, but this time x has to be bigger than or equal to -1. Well, what would that look like? Well, this is still a parabola shifted left 1 unit, so its vertex is at -1, 0. But x is only allowed to be bigger than or equal to -1, so I'm not going to plot the left-hand side of this parabola. I'm only going to plot the right-hand side of the parabola. And this thing is 1 to 1, and therefore it has an inverse. So what's the inverse function? Well, we would do the same thing that we did in the previous section. We're going to switch x and y and then solve for y. Okay, so I'm going to take the square root of both sides. I'm going to have plus or minus square root of x equals y plus 1. So y equals plus or minus square root of x minus 1. Now, we have to make a decision. Is it going to be the positive square root of x minus 1, or is it going to be the negative square root of x minus 1? To make that decision, remember that the domain of the original function has to equal the range of the inverse, and the range of the original has to equal the domain of the inverse. So as far as the domain is concerned, as far as the domain of the inverse function is concerned, it has to match the range of the original. The range of the original is 0 to infinity. The domain of the inverse is going to be x is allowed to be anything bigger than or equal to 0. So the domain, whether we take the positive or negative value, the domain of this function, the standard domain of this is going to be the domain of the inverse. So the domain, we don't have any domain issues, but what about the range? Okay, the range of this function needs to match the domain of the original. Well, what's the domain of the original? It's x greater than or equal to -1, right? So that means the range of this function needs to be bigger than or equal to -1. Well, if I take the positive square root, right, that's a square root function that's been shifted down 1 unit. So if I take the positive square root, then I'm looking at that. This is a function whose range is x bigger than or equal to -1. So this is the function I'm looking for. If I took the negative square root, it would look like this. And this function would have a range of -infinity to -1, which is not the range that we're looking for, right? So I must take the positive square root, right? So it must be the case f inverse of x is positive square root of x minus 1. And you can verify this also by just drawing the graph superimposed over the graph of the original function. And remember that they should have that symmetry that we've talked about, right? So if I graph f inverse of x equals positive square root of x minus 1, so it would look something like this, right? But you can see that when you take the positive square root, it has the kind of symmetry that we're looking for. So so we definitely want the positive square root in this case. Now, you're not always going to take the positive square root, though, right? That's why it's important for you to kind of think things through and reason things out. So let's look at the next example. Okay, same function, f of x equals x plus 1 squared. This time, we're restricting the domain to be less than or equal to -1. So our parent function is still a parabola that's been shifted left 1 unit, but this time I'm only going to graph the left-hand side of the parabola. So this is still a 1-to-1 function. It definitely has an inverse. And if we switch x and y, and then solve for y, then we get the same thing as before, right? Y is plus or minus square root of x minus 1. But in this case, obviously we're not going to take the positive square root, because we saw in part B, if we take the positive square root, that's the inverse of this function when x is greater than or equal to -1. We should be taking the negative square root, but to reason that out, assuming that we hadn't done part B, here's how you would reason that out. You would say, well, I need for the domain of this function, or I need the domain of this function to match the range of this function. That's not a problem, right? The range of this function is 0 to infinity, and the domain of this function is 0 to infinity, so that's fine. But I also need for the range of this function to match the domain of this function. The domain of this function is x less than or equal to -1. That means I need the range of this function to be less than or equal to negative 1. That means I need for this function to go down, right? I need this function to have a range that goes downwards, right? From negative infinity to negative 1. And when you draw that in, right, again, you see that it has the symmetry we're looking for with inverse functions, right? You fold across that red line, and the gray and green halves are going to match up. So that tells us that we definitely need the negative square root, okay? So f inverse of x is going to be negative root x minus 1. Okay, so comparing and contrasting parts A, B, and C I think is going to be really important for your understanding of inverse functions and choosing between the positive and negative versions here, right, of the square root. Moving on, here's a different function, a completely different function. We have f of x equals absolute value of x plus 3 minus 2. This is an absolute value function, so you probably know already that it's not one-to-one, right? It's been shifted left 3 and down 2, but it's still going to have that V shape that's going to cause it to fail the horizontal line test, right? So not one-to-one, and therefore no inverse. But now part E asks us something a little different. It says f of x equals absolute value x plus 3 minus 2, x less than or equal to 0. Well, let's draw this thing. It's still an absolute value function. That's been shifted left 3 and down 2, so there's the vertex. But I'm only going to plot the values of x that are less than or equal to 0. So I think I start here and then kind of work my way back, I guess. So you end up with a function that looks kind of like this. And the question is that thing one-to-one? And the answer is still no, right? This is still not one-to-one, right? It's going to fail the horizontal line test. So this is still not one-to-one. Even though we've restricted the domain a little bit, we didn't restrict the domain appropriately to make this function one-to-one, right? This is still not one-to-one. So there's still no inverse here. Okay. Well, so let's look at another one. Part F is asking us for absolute value of x plus 3 minus 2, x less than or equal to negative 3. Okay. This one I think is going to be one-to-one, right? Because our vertex was at negative 3, negative 2, and we're only plotting the values of x less than or equal to negative 3. So we're only plotting these things, right? So you get this straight line. Holy schmoly, I've done a really poor job of graphing this. There you go. We'll just make that dot really big. Okay, so you're only getting the left hand. It looks like a ray, basically. It's a ray that starts right at that point. That's what we want to find the inverse of. Okay, well, so let's do it. All right, we're going to do the same thing that we did before. We're going to switch x and y, and then we're going to solve for y. So I would add 2, and then to drop the absolute values, I just need to put a plus or minus sign on the left-hand side. So I'm going to say plus or minus x plus 2 equals y plus 3, right? In other words, if the absolute value of y plus 3 equals x plus 2, then that means that either y plus 3 equals x plus 2 or y plus 3 equals negative quantity x plus 2, right, in order for them to be equal. Usually we write it differently than this. Usually we would say something like y plus 3 equals x plus 2, or y plus 3 equals negative x plus 2. If I distribute the negative, I'm going to have negative x minus 2, right? So these are the two options. Obviously, I'm going to have to make a choice between them. But let's finish solving for y. If I solve for y, I would subtract 3. I get y equals x minus 1, or y equals negative x minus 5. So I have to choose which of these functions is going to be the inverse function of this thing that I'm looking for, right? So this is f. Well, so let's think about this a little bit. First of all, I need the domain. Well, the domains of both of these functions are going to be all reals, but I need those domains to match the range of this function, which is not all reals. The range of this function is -2 to infinity, right? -2 to infinity. So that tells me I'm going to have to restrict the domain on either one of these, whichever one I use. I'm going to have to restrict the domain so that I'm only going from -2 to infinity. So here I need for x to be bigger than or equal to -2 in both cases, right? So that the domain of my inverse function matches the range of my original function. So that's the first thing. That still doesn't help me choose which function to use, right? The next thing that I need to do is I need to make sure that the range of this function equals the domain of this one. So the domain of this function is x less than or equal to -3. So if I plug in -2 here, so if I plug in -2, I get -2 minus 1 is -3. And then if I plug in something bigger than that, right, because x can be bigger than or equal to -2, so if I plug in -2, that gives me the smallest output value of -3, right, which is good. But then I need for x to be less than or equal to -3. So what if I plug in something like -1? I get -1 minus 1 is -2. That's not less than or equal to -3. So that tells me I'm probably not going to be using this function. Probably going to use this one. If I plug in -2 here, I have -2, that's +2. 2 minus 5 is -3. Okay, so that's good. Now if I plug in something bigger than -2, like -1, you get -1, that's +1, and 1 minus 5 is -4. That's less than -3. So that tells me that probably this function is the one that I'm going to be using. So I'm going to go ahead and say f inverse of x must be -x minus 5, x greater than or equal to -2, provided that x is greater than or equal to -2. Now just to be sure, we can plot this together with this function and make sure that we get the symmetry that we're looking for, right? So -x minus 5. So I have 1, 2, 3, 4, 5. So it's got this y-intercept. And then it has a slope of -1. And I need to start plotting this starting at x equals -2, right? So okay, so the slope should be down 1 over 1, right? Down 1 over 1. Or up 1, left 1, right? Up 1, left 1. And that's where I start, right? At x equals -2. That's where this function starts, is right there. So I get this function for f inverse. Does that have the symmetry that we want? Well, -3, -3. So the line y equals x looks something like this, right? So are these two graphs symmetric with respect to the red line? Yeah, if you fold across that red line, these two things are going to match up. So sure enough, right, this is my inverse function for this problem. Okay. Very good. So that's how inverses of non-injective functions work. I want to talk about the inverse trig functions now, because these are probably some of the most important examples of inverses of non-injective functions. None of the trig functions are one-to-one. Just take a second and think about the graphs of the trig functions, right? Sine is this sinusoidal wave that repeats over and over again. It's going to fail the horizontal line test miserably, right? Cosine, same thing. Tangent, cotangent, they're these kind of cubic looking things, but they repeat over and over again. they're going to fail the horizontal line test, right? Secant and cosecant, they're these parabolas that repeat over and over. They're going to fail the horizontal. So all of the trig functions, none of the trig functions are one-to-one, right? And consequently, none of them have true inverses. But what we can do is we can restrict their domains so that the trig function on its restricted domain is one-to-one. So here are the standard domain restrictions that we use for each of the trig functions. So for sine, we restrict the domain so that it's between negative pi over 2 and pi over 2. And if you think about why that is, okay, so here's the sine function, pi over 2 and negative pi over 2. The sine function starts at 0, and then it goes up to pi over 2, and that's where it reaches its maximum value. After that, it starts to come down, and so you can see that I can't include any of this because that would make the function not one-to-one. So I can't have any of that. From 0 to negative pi over 2, it goes down to negative 1. Okay, and that's still good. That portion of the graph is one-to-one, but then afterwards it starts to come back up, right? Which would make it not be one-to-one anymore. So I have to snip the function so that it's only between negative pi over 2 and pi over 2, so that I get a one-to-one function, right? For cosine, so this would be for sine, right? For cosine, we do something similar, except that cosine we restrict from 0 to pi. Why is that? Well, because cosine starts at 1 and goes down, right? So at pi over 2, we're back down to 0. From pi over 2 to pi, it continues to go down, so it's still one-to-one on this portion. But if I were to go out to like negative pi over 2, then it would repeat, and you would fail the horizontal line test. So that can't be part of the function. And if I go further this way, that starts to repeat. So this is the snippet that we use for cosine, right? So this is the snippet for sine, and this is the snippet for cosine. So for sine, we're restricting from negative pi over 2 to pi over 2, but for cosine, we restrict from 0 to pi. And you can use a similar line of reasoning to figure out why we restrict the domains the way that we do for each of these functions, right? Tangent's going to be restricted between negative pi over 2 and pi over 2. That's where its asymptotes are, and so you're going to get one copy of the cubic. For cotangent, the asymptotes are at 0 and pi, not negative pi over 2 and pi over 2. So you get one copy of the cubic between 0 and pi for cotangent. For secant, secant is the reciprocal of cosine, so it has the same domain restriction as cosine, except that there's an asymptote in the middle of the interval, right? So it's just not defined at pi over 2. But still, you're restricting your attention basically so that you're between 0 and pi. And for cosecant, it has the same domain restriction as sine because it's the reciprocal of sine, except that it's not defined at 0, right? So they're just kicking out 0. Now, what does that mean about the range of the inverse function? Well, the domain of the parent function is equal to the range of the inverse function. And so the fact that we restrict the domain of sine function to negative pi over 2 to pi over 2 tells us that the range of sine inverse is going to be negative pi over 2 to pi over 2. And the same thing for the other 5 trig functions. This is something that we've talked about in detail in the past, back in chapter 3. We talked about this with inverse trig functions. So for example, whenever you see sine inverse of x, you should know that that's not the inverse of sine x. It is the inverse of sine x with a restricted domain. Okay, I'm calling that f tilde instead of just f to distinguish between these two functions, right? This is sine x on its entire, f of x is equal to sine x on its entire domain, all reals. F tilde is equal to sine x on its restricted domain between negative pi over 2 and pi over 2, right? F is not one-to-one, f tilde is. And so whenever we see sine inverse of x, it's not the inverse of f, it's the inverse of f tilde, okay? So that's sort of a nitty-gritty detail, I guess. But it's not terribly important, except that when you're trying to interpret what sine inverse of some value equals some other value means, like when you're trying to interpret sine inverse of 1/2 equals x, then you need to understand that this means that sine of x equals 1/2, yes, but it also means that x is between negative pi over 2 and pi over 2. And that's how you get just a unique value instead of infinitely many values, right? So even though there are infinitely many angles that satisfy the equation sine x equals 1/2, right? Pi over 6, 5 pi over 6, 13 pi over 6, they all will give you 1/2 when you take sine of those angles. But only pi over 6 satisfies the additional condition that x be between negative pi over 2 and pi over 2. So when you type sine inverse of 1/2 into your calculator, you're going to get pi over 6, and you're not going to get these other values, because this is the only one that lives in the restricted domain. In a similar way, cosine inverse of 1/2 equals x means that cosine x equals 1/2, yes, but it also means that x is between 0 and pi, because that's the restricted domain for cosine. Anyway, we've talked about all this before. I'm not going to make you do a whole bunch of inverse trig functions. Yeah, I might ask you to do a couple in the homework, but for now what I want to do is practice graphing the inverse trig functions. So in order to do this, I'm first going to graph the restricted domain, so or the function with restricted domain. So here I'm going to graph, I'll call this g of x. Here I'm going to graph g of x equals sine x with its restricted domain, negative pi over 2 to pi over 2. Okay, 1, negative 1. So we saw on the previous page that it's going to look something like this, right? At negative pi over 2, sine is negative 1. At 0, sine is 0. And at pi over 2, sine is 1. So it's going to look something like this, right? Okay, so that's what the sine function looks like when we restrict between negative pi over 2 and pi over 2. So then what does the sine inverse function look like? Well, we're just going to swap the coordinates, right? Like we do for any inverse function. Instead of going through the point pi over 2, 1, it's going to go through the point 1, pi over 2. So 1, pi over 2. Instead of going through 0, 0, it's going to go through, well, 0, 0, right? You switch the coordinates, you still get 0, 0. And then instead of going through negative pi over 2, negative 1, it's going to go through negative 1, negative pi over 2. Right, so it's going to go through that point. And then also imagine that you take this function, and remember you have to have this symmetry. You have to have this symmetry with respect to the line y equals x. Oh, actually, that was badly drawn. So really, I guess it would look something more like. So pi over 2 is like 1.5 or 1.6, something like that. So it would be 1.5. 1.5 would maybe be up here somewhere, and so really the line y equals x, looks something more like this, I suppose. But still, the idea is you need to imagine flipping this around that line. Okay. So if you do that, you know that you're going to get this this sort of mirror like this, right? So the shape of this function, instead of doing what the sine function does, right? So instead of looking like this, it's going to concave down instead, like that. So that's what the sine inverse function looks like, something like that. Okay, so let's see if we can do the same thing for cotangent inverse. Cotangent inverse. Now, we said that we would restrict the domain between 0 and pi. So here I'm going to graph g of x equals cotangent x. X is between 0 and pi. So maybe I'll say the domain here is going to be 0 to pi over 2, union pi over 2 to pi. Just because because we're going to have asymptotes, an asymptote at pi over 2. So 0, pi over 2, pi. Wait, do we though? No, this is not correct. Yeah, the domain is just 0 to pi. I don't know what I must have been thinking about a secant. That's what I was thinking. I was thinking of the secant function or the cosecant function. But no, for the cotangent function, no, the domain is just 0 to pi. Okay, my apologies. Anyway, but you have asymptotes at 0 and pi. Whoops, this is pi. This is pi over 2. And then at pi over 2, cotangent of pi over 2 is 0, right? And then remember, cotangent falls, so it doesn't increase, it's a decreasing function. So it goes more or less like that, right? So that's what one copy of the cotangent function would look like. So now the cotangent inverse function, we're going to replace pi over 2, 0, and we're going to plot 0 pi over 2. So so maybe pi over 2 is there. So it's going to go through the point 0 pi over 2. We're also going to have, instead of these vertical asymptotes at 0 and pi, we're going to have horizontal asymptotes at 0 and at pi. Okay, so here's pi, pi over 2. And then what does the function look like? Well, if you imagine sort of flipping this thing across, flipping this thing across the line y equals x. What's it going to do? So if I flip this down, I think this thing ends up, so this top part ends up going off this way, and this bottom part ends up going off this way. So we get a picture that looks something like that. I suppose I could verify that. Like, I know that this is going to go through pi over 4, 1. That means this should go through 1 pi over 4. Yeah. And this thing's going to go through 3 pi over 4, negative 1. That means this thing should go through negative 1, 3 pi over 4. Right? So yeah, so definitely doing this kind of falling motion. Still a decreasing function. Okay, so there's cotangent inverse. Then let's do secant inverse. So again, before I can do secant inverse, let's look at what secant looks like when I restrict the domain. So I'm going to graph secant x with its restricted domain. This is the one I was thinking of. So secant has the same domain restriction as cosine, right? That is, it's going to be restricted between 0 and pi, except that it has an asymptote in the middle at pi over 2, right? So it's going to go from 0 to pi over 2, and then from pi over 2 to pi. So let's put in the asymptotes, right? At 0, pi over 2, 0. It doesn't have an asymptote at 0, though. It has an asymptote at pi over 2. In fact, the secant function usually has an asymptote at negative pi over 2 as well, and then you get this parabola. But you can tell why you're not going to be able to graph the whole parabola, because that would make the thing not 1 to 1, which is why you're only graphing from 0 to pi over 2. That's y equals 1, by the way. And y equals negative 1. So from pi over 2 to pi, you're going to have the left half of the bottom parabola. And so this is what the function looks like with its domain restricted. So you get the right half of the parabola going up and the left half of the parabola going down. Okay? But this is a one-to-one function now. If you graph any more, then it's going to start to go down, and that's not going to be one-to-one, or it's going to start to go up, and that's not going to be one-to-one. So that's why this is the domain restriction that we use. Now, what is the secant inverse function going to look like? Well, first of all, we're going to have a horizontal asymptote at pi over 2. Right, pi over 2. Second of all, it's going to go through the point, instead of going through 0, 1, it's going to go through 1, 0. And instead of going through pi, negative 1, it's going to go through negative 1, pi. Okay, so we know that much. And now if we imagine flipping this thing across the line y equals x, so flipping it like this. If you can imagine flipping it over, this thing is going to end up going down, kind of like this, right? So so that's this one right here. So it's going to go down like that. Oh, is that right? No, it's got to be getting closer to the asymptote, right? So what's going on? If I flip it over, that seems right. If I did something like pi over 4 something bigger than 1, so then I have something bigger than 1 pi over 4. It must be going, so I'm leading you astray. It must be getting closer to this asymptote. So it's not this part down here. I'm having a hard time visualizing it though for some reason. If I flip this, do these not match up? Oh, they don't. No, it goes like this. There we go. There's the symmetry we're looking for, right? If I flip that over, then they match up. Yeah, okay, I apologize. I was just having a hard time seeing it for a second. But no, it goes up. It goes up. And this one, then it must go down toward the asymptote as well, kind of like that. Okay, so this is what the secant inverse function looks like. So there you go. Now in the homework, you're probably gonna I'm gonna ask you to graph translations of the inverse function inverse functions. My advice would be, if you're confronted with a transformation of one of these things, just graph the original function first, so you have a good idea of what it looks like, and then worry about shifting it around. Okay. So that's that. That's all I'm going to say about inverse functions. I think I've said enough, right? We'll see you in the next section.